All right, Algebra 2, our very first video, an introduction to functions. This is a section not found in your textbook. This is actually a review of junior high and Algebra 1 skills that we're coming back and revisiting before we dive into this idea of a function in Algebra 2. So our objective for this lesson is to be able to identify and describe a function verbally, algebraically, verbally, that just means they're with words, algebraically, graphically, and using function notation. We should be able to find and describe the domain and range of a function and use function notation to find an output or input of a function. Okay. So a lot of the stuff we may not remember, that's why we're doing this lesson. So first of all, we need to know about a relation. What is a relation? This idea of a relation right here. Okay. So a relation is really just what we call a relationship between two things. And these things we'll call sets. So let's say over here I have a bubble, a set of stuff over here. I have a set of stuff over here. And basically these things are connected to these things over here. Okay. So basically I have two different, it's what we call a relation. Okay, is when we have those two things relating to each other. Okay. So really, as long as you have, one set here relating to another set, any way they're related, it's called a relation. Okay. Now, if every input, okay, and let's talk a little about the vocabulary. These things over here in this area, we call inputs. So let's go ahead and let's label those that way. Call those inputs. And these over here, we call outputs. Okay. So I kind of like to think of it as a bit of a machine, meaning you put something in here, over here, it does something to it, and then you get something out over there. Okay, so a function is a special kind of relationship. So a function is a special kind of relation. Really, all it does is it takes this idea of a relation up here and puts a few little rules on it. Basically what it tells me is that every input value can go to only one output. Okay. I always like to think of like some examples, like how can we kind of get examples here. So really one example of a relation that's not a function is if we look at the idea of siblings up here. Siblings would be a relation, but not necessarily a function. Because let's say if someone had two brothers. So if I put them in, and I was like, okay, well, who's his brother? Well, you can name me two different people. So that input has more than one output, okay? Now, but something that would be a function would maybe the idea of age. If I said, okay, how old is someone? They're only one age, like they can't be both 18 and 25, okay? They're only one thing. So every input can go to only one output. And I, a lot of times, like to think of a function as a machine. So here's my little machine here. So I'm going to come in and I'm going to put stuff into this machine. There's my input. And then it's going to spit some stuff out, which will be here, my output. Okay. Our input has a special mathematical name. We refer to it as the domain. So the domain is the set of all possible inputs. For example, if I was doing everyone in this classroom and I was putting you in a machine and it was spitting out your age, my domain would just be a list of everyone in this room, okay? Where the range, this range is all the set of all possible outputs. So again, with that age idea, if we're looking at, again, everyone in this room and their ages, okay, you guys are all younger than me, so let's say we go down, the youngest person in this room is 15, so it would be the ages from 15 up to my age, which is 35. So that would be my range, the ages 15 to 35. Whereas my domain over here would be a list of everybody in the room. We put someone in, so we would put someone in, we would put someone in this machine and it would spit me out their age. That's a function. Okay. All right. So now let's go ahead and let's look at this example 1. So here they give me the function in words. They tell me to multiply the input by 2, then subtract 1 to get the output. So this is a mathematical function. Not all functions are mathematical, but this one is. So I want to create a table for this function. So a lot of times in mathematics, our input, it's easier to refer to our input as a variable. So I'm going to use x for my input and y for my output. So I'm going to create an input-output table. So we're going to do a bit of a t-table here. So let's go x's. This here is my inputs. And then we'll do y's here. Those are our outputs. Okay. So it doesn't tell us what numbers to put in. We just want to create a table so we can pick whatever numbers we want. So I'm going to start with my favorite number, the number 2. So it says to multiply the input by 2. So I need to take 2, multiply it by 2. So 2, multiply it by 2, and then subtract 1. 2 times 2 is 4, subtract 1, we get 3. So when I have an input of 2, I have an output of 3. Let's put another number in. Let's see, let's pick the number 7. So multiply the input by 2, so we'll take the 7 times 2 and then subtract 1. So 7 times 2 is 14 minus 1, 13. So when I put an input of 7, I get an output of 13. Okay, here, let's go. Let's do a negative 1. So we have negative 1 times 2 minus 1. Negative 1 times 2 is negative 2 minus 1 is negative 3. And we'll do one more. We'll put in a 0. 0 times 2 minus 1. 0 times 2 is 0 minus 1 is negative 1. Okay, so here's my table. Here's my list of inputs. And then over here's my list of outputs. And then here's my work to get to those outputs. So since these are my x's and these are my y's, I can actually graph these on a graph. I can think of this as an ordered pair where x is 2, y is 3. So I can graph that point. Remember, we go over 2, up 1, 2, 3. So there's my 1 point right there. Okay, for this one, input of 7, so that's my x, output of 13. 7, 13, 1, 2, 3, 4, 5, 6, 7, 5, 6, 7, 8. Way up here. There's my point right here, so we'll go ahead and erase all of these points. Those were just me counting. Okay, and then we'd have the ordered pair negative 1, negative 3. 1, 2, 3. And there's the other point, and then the point 0, negative 1. Okay, so we're just graphing these lines. Sorry for the clicking. Okay, so there I represented here. The function is represented in words, so verbally. Here it's represented in a table, which then I can write as what we call ordered pairs. Again, these are ordered pairs. So then I can graph those ordered pairs. Over here is a graph. But then now I can actually write an equation for this function. Because what we did over here is we took my input value. So here my x is 2. We multiplied it by 2 and then subtracted 1. So I can think of that as I take my input value. So I can think of this as x times 2 minus 1. Here we'd have x times 2 minus 1. So I could write this as x times 2 minus 1. And that ends up giving me over here my y value. Gives me my y. Okay? So we normally write 2 times x is 2x minus 1 equals y. We tend to like to write the y on the side. I don't know why, it's just how we prefer to do it. So there is my equation of this function. So this is what we call the equation or rule for my function, because I can just look at this equation. I could write it in words. I could have these words right here, these words. I could, if I was referring to this function, I could tell you to just multiply the input by 2 and then subtract 1 to get the output. Or I could have you write this instead. This right here is shorter than writing this all out. This right here is easier to say. So that's why we tend to like equations. Mathematicians like the shortest, most concise way of writing things. So writing it as an equation is way shorter than writing it in words. Okay. All right, so now we have something. Now we need to talk about something. Now that we know about the rule, we can go ahead and write this in what we call function notation. Okay, so what that means is now instead of writing y equals, we give functions a name. We give them a name. Ooh, I don't know what I was writing there. We give them a name. Okay. This name is usually a letter of the alphabet. Most often we use the letter F, but a lot of times we also use a G or an H or a K. For some reason, those are the ones we tend to like the most often. The ones we use, kind of like how we always use X and Y, when really we could use any letter. We use F, G, H, K, M. We tend to not use L or O. Those look like ones or zeros, like L and O. We don't use those. Okay. But we give them a name, and we use that name to write the equation. So like up here, we have this rule, y equals 2x minus 1. Basically, what function notation does is it replaces the y, and it uses the name instead. So instead of writing y equals 2x minus 1, we'd write f of x equals 2x minus 1. So really, all we did is we replaced this y with this f of x. Okay, and what this, and this is red, we read this as f of x. What this tells me is f is the name of the function, and the x tells me what my input is. So this gives me my function's name is f, and I put x into the function. X is my inputs. Okay, so that's how we use function notation. So if I see, let's say f of 3, what this tells me is this tells me I want to put a 3 into the f function. So if this is my f function here, 2x minus 1, this tells me I want to replace this x with a 3. So I'd replace this x with a 3. Basically, I'm putting a 3 into this function, like up here in my table. I put a 3 up here and take 2 times a 3 and then subtract 1. So when it's asking for f of 3, it's asking me to put a 3 into that function. So I'd write 2 times 3, subtract 1. 2 times 3 is 6, subtract 1 is 5. So f of 3 is 5. Okay, so f of 3 is 5. This tells me when I have an input of 3, I have an output of 5. So a lot of times we'd write it again this way, f of 3 equals 5. So basically this is shouting at me, hello, that's my input. And the 5 here, that's my output. Kind of overlapping there. So the 3 is my input, the 5 is my output. So basically this is telling me I have the order pair 3, 5. Comma, with the comma, not 3.5. Okay. All right. Okay. So in the function rule from example 1, what input would be needed to produce an output of 17? So if we look back at that example, okay, example 1, so here's my function, f of x equals 2x minus 1. So let's write that down, f of x equals 2x minus 1. It's asking me what input would I need. It's looking for what do I put in here for x so I get out that 17? Okay, so we want to get out a 17, so we want this thing to equal 17. Basically, I'm looking for what x do I put in here when I take 2 times x subtract 1 that I get 17. Okay, so one way of doing this is using our Algebra 1 skills of solving equations. So I would add 1 to both sides. 2x equals 18. Then divide both sides by 2. X equals 9. So I'd have to put in a 9 for my x to get out a y. So my input, this is telling me 9 is my input. All right, so example 3. Given the function f of x equals x divided by 3 plus 7, do the following. Explain what the function rule does to convert the input into an output. So it says explain, so I better have some words here. So it looks like, let's see, this is f of x equals x. It takes my x and divides it by 3 and then adds 7. So let's write that out in words. It's going to take my input. Input is divided by 3. Then add 7. So that's what it does, the input to get to the output. So now it wants me to evaluate f of 6. All this is telling me wants me to put a 6 into this function for my x's. So I would find f of 6, so show my work. I would take 6 divided by 3 and then add 7. So 6 divided by 3 is 2 plus 7 is 9. So I would write f of 6 equals 9. Write it just like that. And find f of negative 9. So let's find f of negative 9. Negative 9 divided by 3 plus 7. Negative 9 divided by 3 is negative 3 plus 7 is 4. So I'd go f of negative 9 is 4. Basically, this is telling me when I here have an input of 6, I have an output of 9. When I have an input of negative 9, I have an output of 4. Okay? C, find the input for which f of x equals 13. Show the work that leads to your answer. So I'm trying to find when does f of x, and f of x, again, is this guy right here. That's my f of x. I want to know when does that thing equal 13. So to find that out, I'm going to set that equal to 13. We'll take that x divided by 3 plus 7. I want to know when does that equal 13. So first thing I'm going to do is I'm going to subtract 7 from both sides. So I'd have x divided by 3, 13, subtract 7, so 3 is 10, so 4 more 6. Okay, let's take it over here. So I now have x divided by 3 equals 6. So to get rid of divide by 3, we need to multiply both sides by 3. Again, these are just some Algebra 1 skills. So x equals 6 times 3 is 18. So when I put an input of 18 into this function, I get an output of 13. And you can try it. Come back up here in the original function and see. X divided by 3 plus 7. If I take 18 and divide it by 3, I get 6 plus 7 is 13, so it did work. Okay. Now, if g of x equals 2 f of x minus 1, well, in mathematics, we know if there's nothing written between a number and something, it's a multiply. So this is taking 2 times my function f of x and then subtracting 1. Then what is g of 6? So this is basically saying g of x, that's a new function, a function whose name is g. So this g denotes the function's name. And the x tells you what your input is. So I'm still inputting an x. Okay, so I'm putting a g in. Sorry, my name is g. I'm inputting x. Okay, so what I do is I take my f function, multiply it by 2, that's this 2 right here, times my f function, and then when I'm done, I want to subtract 1. So to find g of 6, the first thing I need to do is find f of 6. So I need to take 2 times f of 6 and then subtract 1. So to find f of 6, I'm kind of out of room down here. Sorry guys, I'm a little cramped. To find f of 6, I need to go my f function, which is x divided by 3 plus 7. So I'd have 2 times 6 divided by 3 plus 7. And then I want to subtract 1 from the end. So, but I want to do this thing first. So let's see. 6 divided by 3 is 2 plus 7, 9. So we'll have 2 times 9 minus 1. 2 times 9 is 18 minus 1, 17. So I would get 17. So g of 6 is 17. I would normally show this work straight down, but I'm kind of out of room. Okay. All right. Let's see next one. Okay. Oh, sorry. I don't know what that was. Okay. A function rule takes an input n and converts it into an output y by increasing 1/2 of the input by 10. Determine the output for this rule when the input is 50, and then write an equation for the rule. Okay, so it wants to take an increase, that means go up, that's an addition word to me. Half, to me, that's dividing by 2 of the input by 10. So I want to, by increasing 1/2, so I want to take half of the input. So I want to take half of the input, that's right here in words. Half of the input, and then I want to increase by 10. Okay, so it says determine the output for this rule when the input is 50. So if my input's 50, I want to take half of 50. So I want half of 50, and then I want to increase it by 10, add 10. So half of 50 is 25, add 10, which is 35. So I kind of went from words, and then there's kind of just mainly words, and then a mix of words and some symbols, and then just plain symbols. So we get 35. So the output is 35 when the input is 50. So now we want to write an equation for this rule. My output is y, so this guy right here is my y, equals, and we're adding 10 to half of my input. So how would I denote half of my input? There's really two different ways of doing that. You could do half times my input, or I could do take my input divided by 2. And we tend to like our y on this side. So either one of these would be okay. Okay. They both mean the same thing. You're both going to get the same thing out regardless of which one you do. Okay. Function rules do not always have are numerical in nature. Sometimes they're just words instead of numbers. They simply have to return a single output for a given input. So here we have a table that takes as an input a neighborhood child, and as an output it gives them the month he or she was born in. So here I have Max. Max is the child. When I put Max into that machine, I get out January. When I put in Evan, I get out April, so forth. Is this rule a function? Explain. First of all, does every input, so here's my inputs right here, let's label those. Here's my outputs. Does every input have only one output? Is there any way I could input somebody from over here and get more than one thing over here? I gotta think. We're inputting children, getting out the month they were born. So to me, if we think about it, is there any way any kid could be born in more than 1 month? Nope, they're only born in 1 month. Only 1 month. So, is this rule a function? Yes, it is. Because every child is born in only 1 month. Oh, that one looks bad. Let's erase that. Do a 1 that way. Okay. What is the output when the input is Rosie? So let's look at my inputs here. My inputs, let's find Rosie. My output would be February. Okay, what is the domain? Well, if we remember from previously, let's go back in our notes and look. The domain is the set of all possible inputs. So really, I just need to list out all my inputs. Oh, too far. So my domain, so we'll just list my domain. And we'll do a set is Max, comma Evan, comma Zeke, comma Rosie, comma Nico. Okay. And then my range is January, Let's list these least to greatest, but it doesn't matter. We'll just go January, April, May, February. Oh, I don't need to list May again. May's already in that list. You don't need to list things more than once, even if they happen more than once. So yes, there are 2 Mays. There's this May and there's that May, but it doesn't matter. That's still a function, and because every input only goes to one output. It doesn't matter if it goes the other way around. Okay, and I only have to list May once, even though it happens twice. We only list each thing once. That's just how functions work. Okay, all right, next example. Okay, now we're going to be looking off a graph. Okay, so here my function y equals f of x is defined by the graph. So this graph shows my function. Okay, it is known as a piecewise linear function. It's made up of straight lines, so all these lines are just nice, straight, and it's broken up into pieces. There's this piece here, and that one there, and that one there, and that one there. So that's why they call it a piecewise linear. Answer the following questions based on this graph. So we want to find now f of 1. So this means when I have an input of 1. So I like to remind myself this is my x, and I want to try to get my y out. So when my x is 1, so let's come over here and let's look. When x is 1, y is 1, 2, 3, 4. When x is 1, y is 4. So really it's this dot right there. Okay, so now f of 5. So again, this is my x. So let's come over and let's look for f of 5. 1, 2, 3, 4, 5. Down here at -2. So it's -2. So that's this spot right there. Now f of -3. So let's come over here. We're looking at -3, back 1, 2, 3. F is 1, 2. -4. So when x is -3, y is -4. And now f of 0. So now we have a 0. It's 2. So again, these points would be this guy here and that one right, oh no, that one right there. Let's erase that one. Okay. Now solve each of the following for all values of the input x that make them true. So now this is backwards. This is telling me my output is 0. It's looking for my input, so I'm looking for my x's. My x is equal to, so what x's have an output of y? So output of 0. So I'm looking for 0 as an output. So I want to be up and down 0. So if I want to be up and down 0, hey, let's see. It looks like it's going to be, let's see, up and down 0. So that means I want to be on this line right here. So let's see, that would be this point right here, this point right there, that one, and that one, and that one. That'd be an x of -1, an x of 1, 2, 3, 4, 5, 6, 7, because it would be this point right here, because that's got a y of 0, this one has a y of 0, and that one has a y of 0. So now we want a y of 2. Let's see, let's go green. So now I want a y of 2. Again, that's my y, because this is my y. Y is 2. So now we want a y. Let's go to my y-axis. Again, this is my y-axis right here. We want a y of 2 right here. So I'm looking for anything on that line right there. So where is my y? 2. So it looks like it's this point right here and that one right there. So it'd be at 0 and 3. Okay, so it looks like here we're at x, where x is 0, and where x is, what did we say, at 3? Okay. All right, what is the largest output achieved by the function? At what x value is it hit? So if we're looking for the biggest output, so I'm going to go ahead and I'm going to kind of erase some of my marks on my graph here. So looking for the biggest output. Again, my output here, to remind myself, my output is my y's. So I'm looking for where's my y the biggest. Again, y is up and down. So if we want to know where do I go up the most, if we look, this is the highest spot right here. So it looks like it's at, where is that? There's 0, 1, 2, 3, up at 4. So the largest output is a 4. That's the highest we'll go, and that happens when x is where? When x is right here at 1. So the largest output I get is 4, and that happens when my x is 1. Okay, so now we want to find the domain and range. I didn't really leave a lot of room here, so I kind of have to squeeze that in. Okay, my domain. Again, my domain here is my inputs. That's your x's. So I want to come look at the graph, okay, and look at my x's here and figure out what x's do I have. So we're looking at my x's right here. And so if I look at my x's, I come down and I have x's all the way down to here because I have an x right down here. So all the way down to here. And then I have x's, I have stuff on x's here, on x's here, on x's, all the way up to here. So really, as far as x's go, if I only saw from here to here, I'd see my entire graph. So that tells me my domain goes from -1, 2, 3, up to, let's see, where are we at up here? Up to 1, 2, 3, 4, 5, 6, up to 8. So my x's go from -3 to 8. So there's my domain. My domain go from -3 to 8. So we can write that in interval notation. My x's go from the lowest at a -3, highest to an 8, and we equal both -3 and 8, so we can put equals there. -3 is less than or equal to x is less than or equal to 8. Or you could write it in words. My domain is all the numbers in between -3 and 8. Okay, now let's look at my range. So let's go ahead and pick a different color. Let's go red. So my range again is my y. So we already know my tippy toppest I get up here is a y of 4. The lowest I get is down here, and that's a y of -1 to -4. So really my y's go up from +4 to -4. So my y's, so that would be my range, go from -4 to +4. My y's would be in between, and we equal those values, so that doesn't look very good. So we'll write it that way. Again, you could write it in words as well. My range goes from -4 to 4. Okay, all right, next one. Last one, I promise. Okay, all right, so I'm gonna read this problem to you, and then this is what I'm gonna call my your turn problem. I want you to attempt this problem as best you can, and then we'll get into groups and go over it so you can tweak your answers a bit. Charlene heads out to school by foot on a fine spring day. Her distance from school in blocks is given out as a function of time in minutes. She has been walking. This function is represented by the graph given below. So here in this graph, again, my input here is time. She's been walking. My output here is the distance from the school in blocks. Again, this isn't the distance she's traveled, this is how far she's away from the school. So I want you to go ahead and answer A, B, C, D, and E, again, as best you can. We'll tweak them in groups when we get back to class. Okay, we'll go ahead and find a partner and do them. Okay, but I want you to do that as best you can and bring that back to class. Good luck.